Okay, third and final part, dealing with volumes of known cross-section, or VSKSC for short. We've been working through the worksheet that I've made, and we have three more problems. We have 7 and 8 on the original worksheet, and I want to show you an example of it being perpendicular to the y-axis, so we'll do that one last. But let's go and look at 7. I think this is the last type of cross section where we need to figure out the area formula. This one is extremely easy though, okay? We're doing isosceles right triangle with hypotenuse down. So, isosceles right triangle. Actually, let's not do hypotenuse down. Sorry, I thought this one was supposed to be. Let's do it with the leg down, okay? Because whereas hypotenuse down looks like this, right, with the right angle pointing up, this one with the leg down looks like this with one of the legs being the base, okay? And it's just a little bit different, and I'll show you that here in just a second. But we're going to be doing it for y is equal to secant x, y is equal to 2. Now that obviously happens, the intersection of those two graphs happens an infinite number of times. But we're going to focus on just the region between negative pi over 2 and pi over 2. Remember, they actually meet at negative pi over 2 and pi over 2, because cosine of negative pi over 2 is 1/2, the reciprocal of which is 2, and cosine of pi over 2 is 1/2, the reciprocal of which is 2. Actually, but not negative pi over 2 to pi over 2, but you get what I'm saying. We'll actually look at it right here. Now, if we look at y is equal to secant x, okay, and forgetting the mistake that I just made, we're actually going to have to find those points of intersection, okay. And it's actually not pi over 2. I misspoke. It's pi over 3. Because remember, cosine of pi over 3 is going to be 1/2. Remember, in the first quadrant of the unit circle, right? We have 60 degrees, which is pi over 3, 45 degrees, which is pi over 4, and 30 degrees, and that's horribly off, but you understand what I'm talking about. And cosine of these, cosine of 0 is 1. Cosine of pi over 3 is root 3 over 2. Cosine of pi over 4, which actually should be more right here, is root 2 over 2. And cosine of pi over 3 is 1/2. So cosine of pi over 3 is 1/2. So cosine of plus or minus pi over 3 is 1/2. That means the secant of plus or minus pi over 3 is the reciprocal, or 2. So that gives us our limits of integration. That's really all that we really had a problem with. Now, we have to deal now, so we have our limits of integration. We know that it's going to be 2 minus secant x is going to be our s, right? So that's the second piece of information that I need. That one was actually rather easy. It's the top minus the bottom. Now I simply need my area formula for an isosceles right triangle, isosceles being the key word, right? An isosceles right triangle with leg down instead of hypotenuse down. Well, instead of being 1/4 of a square, it's actually just 1/2 of a square. So the area of this is 1/2 s squared. Well, now I have everything that I need. I have my limits of integration, okay, negative pi over 3 to pi over 3. And of course there's symmetry, and I could go from 0 to pi over 3 and double it, but let's not worry about that right now. 1/2 s squared dx. And that's it. Okay? Really, really easy. I'm not even going to evaluate this one. We're going to go ahead and move on to the next one so that we don't get crowded for time on this last video. But you guys know how to push buttons in your calculator. You knew that before I met you. Okay? Let's go ahead and look at number 8 on the worksheet. Number 8 on the worksheet is y is equal to 1/2 sine x, and y is equal to negative 1/2 sine x. So a vertical shrink and vertical shrink and then a vertical shrink and a reflection. And again, because it's periodic, that happens an infinite number of times. I'm only interested, in the interval between 0 and pi, and I want cross sections that are semicircles. So let's go ahead and look at that. We see the fact that this up here is y is equal to 1/2 sine x. This down here is y is equal to negative 1/2 sine x. I know that my cross sections are going to be perpendicular to the x-axis. I know that my side, my s value, is going to be 1/2 sine x minus a negative 1/2 sine x, or just sine x. Okay? Now, I know that the area of a semicircle, because I've done this one before, is pi over 8 sides squared. So that actually becomes pi over 8 sine squared x. I know that my interval is going to be 0 to pi. 0 is right here. Pi is right here. Since one of the functions is a reflection of the other, neither of them have a period change. I know that their intersections are going to be half a period apart, 0 and pi. Let's go ahead and put the pi over 8 out in front. Sine squared x dx. And if you're wondering how to do that by hand, you're going to need the power reducing formula. Trig ID that we learned last year. So power reducing in order to turn sine squared and cosine squared. By the way, those of you that are BC are going to need those identities when you get to chapter 7 in the Stewart book, which is for techniques of integration. So anytime you have sine squared or cosine squared, you can use the power reducing formulas to get it into something that is actually integrable. Okay. Again, I'm not going to go ahead and do this one. I want to save a little bit of time to explain the one that is perpendicular to the y-axis, and also to summarize all of the area formulas that it's probably a good idea that you should memorize. Now the last one that I added to this worksheet, which wasn't originally part of it, obvious from the fact that it is handwritten, and handwritten rather recently, I want to do y is equal to 2 root x, and y is equal to 2 cube root of x. Now that gives us a very distinct area, and I'm going to show it to you in just a second. I want to do it for equilateral triangles, and I want it perpendicular to the y-axis. So let's go ahead and take a look at that. Now, I know that when I'm doing this, this one right here is y is equal to 2 root x. Okay, I know that this one is y is equal to 2 cube root of x. The reason that I know that is just take any value between 0 and 1. Take, I don't know, 1/8. If you take the square root of 1, or let's take 1/4. If you take the square root of 1/4, it's 1/2. If you take the cube root of 1/8, it's 1/2. So the cube root between 0 and 1 is going to ascend to a higher output much quicker because it's going to get, it's the opposite of the fact that it's squaring. Because remember, when you have x squared and x cubed, of which, these are transformations on the inverses of those, when you square a number between 0 and 1, it gets smaller. When you cube a number between 0 and 1, it gets much smaller, okay? So the behavior of x squared and x cubed behaves differently between 0 and 1 than it does between 1 and infinity. Well, the same thing with their inverses and the transformations thereof, okay? Now remember, I don't want to do it with vertical cross sections. I want to do it with horizontal cross sections, and I know that this is going to wind up being a width of dy. That means that I need my integrand as a variable expression in terms of y, and I need my limits of integration in terms of y. Well, it just so happens that it's very, very easy to get my limits of integration. 0 to 2 ought to do just fine, okay? So I know on y, I go 0 to 2. Those are my limits. Well, I'm going to need to transform both of these right here. Well, if I have y is equal to 2 square root of x, y over 2 is equal to the square root of x, or x is equal to 1/4 y squared. If y is equal to 2 times the cube root of x, I'm going to get y over 2 is equal to the cube root of x, and I'm going to get x is equal to 1/8 y cubed. Well, that means that this one is x is equal to 1/8 y cubed. That means this one right here is x is equal to 1/4 y squared. Now remember, when you're dealing with respect to y, it's the more positive one minus the more negative one. We're no longer dealing with top minus bottom. We're dealing with right minus left. So my s is going to be 1/4 y squared minus 1/8 y cubed. Now I'm dealing with equilateral triangles, and so I know that my area of equilateral triangles is √3/4 s squared, and now I have everything that I need in order to integrate. I go from 0 to 2, I pop the constant of that area formula out in front, I transform s into its variable equivalent in terms of y, I square it, tack on a dy, and of course I think you know how to push buttons, so I'll trust that you're able to actually plug that in and discern the actual answer. Now, before I draw to a close our discussion of volumes of solids of known cross-section, let's go back and very, very quickly talk about the area formulas. Now, the first one that we did, because remember, all of these, the square one, is basically a square prism, right? But the width of the prism is the differential. It's the dy or the dx. So the area of a square is simply s squared. Very, very easy. Well, the semicircle was a little bit more difficult, okay? Simply because you had to transform the radius into the diameter, and it's a semicircle and not a circle. So it wound up being pi over 8 s squared, right? Where this right here is s and this right here is s. Well, isosceles triangle with the hypotenuse down means that the right angle is sticking up in the air, okay? Well, the area winds up being what? Well, it winds up being 1/4 of a square. Well, isosceles right triangle with the leg down winds up being a little bit even easier than that, because if this is s, sorry about that, the area of this is half of a square. The last one that I actually need to mention is the equilateral triangle one. We broke that down, we went ahead and dropped a altitude and talked about it in terms of 30, 60, 90 right triangles, and surmised that the area was √3/4 s squared. The only other ones that you're likely to see are perhaps rectangles, but they're basically squares just with a coefficient tacked off out in front because they have to actually tell you the relationship between the height and the width. And it's basically, side times some coefficient of the other side. But those right there are the five that you really need to know, I would just memorize them. Now, the only two that are actually the least bit difficult are, of course, this one and this one because they're kind of bizarre coefficients, pi over 8 and root 3 over 4. But if you do enough problems, you'll wind up sort of getting the hang of that. So that brings to a close our discussion of volumes of solids and no cross sections. Be on the lookout for our discussion of 6.5, which is average function value, and the intermediate, or the mean value theorem for integrals, which actually ought to be rather straightforward. So look for a couple of videos on that, probably not too many. Bye.